Hey everyone, so today we're going to learn about optimization. Basically, optimization is finding maxes and mins via the first derivative test, but also with word problems. So the reason these are a little tougher is because there are words and they're not just straight up find the first derivative, find the maxes and mins. It's going to be written as find the maximum or find the minimum, product or least amount of fencing are the two we're going to start off with. So basically what you want to do, first of all, identify, just like any other word problem, identify all the quantities to be determined. We're going to write a primary equation that needs to be maximized or minimized. And then you'll probably want to use a secondary equation of some sort so that we can substitute in. So we only want one variable in this primary equation. So if there's more than one variable, we'll just be replacing it with some secondary ideas. So let's try it out. Find two positive numbers where the sum of the first and twice the second is 100, and the product of the two numbers is a maximum. So wherever you see that word maximum, okay, or minimum, or whatever you're trying to maximize or minimize, that's going to be your primary equation. So your primary equation is, in this case, the product of two numbers. So I'm going to say P for product is x times y. So we'll use x and y as the two numbers. Okay, so if you want to define kind of your two numbers, you could say x is the first number, y is the second number. Okay, and then there's this other thing, right? Because we can't take the derivative of this with, we have two variables right now. We want to make it a little easier for ourselves. So this whole first part, it says the sum of the first and twice the second is 100. So that's going to be one of our secondary equations. So secondary equations are just other pieces here, other information, not the thing we're trying to maximize, but things that might help us. So first plus twice the second is 100. Okay, and now it's kind of back to like algebra 1, I guess, where you're doing substitution. So solve for x or y. I'm going to solve for x, it's a little easier. And I'm going to take this, okay, and plug it in for x. So now instead of p equals x times y, I have p equals 100 minus 2y times y. All right, and then probably you want to FOIL it so that we can take the derivative pretty easily. So that gives us 100y minus 2y squared. All right, and again, like I mentioned, optimization is still finding maxes and mins, aka using the first derivative test. So we're going to take the derivative, p prime, we get 100 minus 4y. We set it to 0 to find the critical numbers, and we get y is 25, excuse me. So to check if that's actually a maximum, okay, we would do p prime, 0, infinity, it said positive numbers, 25 is our number. We plug into p prime, which is 100 minus 4y. If we plug in something between 0 and 25, we would get a positive. 25 to infinity, we would get a negative, meaning P, our product, is increasing and then decreasing, so 25 is a max. So you don't necessarily have to show this work, but I think that is a nice way to check if you're correct. And your final answer is, it says find the two numbers. Okay, well, y is 25, we already found that. And then x is, take 25, you could plug it in anywhere. I guess I'll plug it in here, 100 minus 2 times 25. Which is 50. So x is 50 and y is 25. All right, that is the first example there. And let's try out the second one. It says a farmer plans to build a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing? Least amount meaning the minimum amount of fencing if no fencing is needed along the river. Okay, well, first of all, least amount of fencing, we're talking about perimeter here, right? The perimeter of this pasture or, whatever we're using for fencing, that's how we'd find how much fence we need. And that is going to be the primary equation, okay, is going to be perimeter. But let's figure out what this looks like. You can use your art skills over here. Here's a river. And then the pasture is adjacent to it. It says, one of the sides is contained by the river. Okay, so this would be my fencing. Fencing, and it says it doesn't, the river would just hold back, the cows or whatever. Whoever's in this pasture. Okay, so that's the amount of fencing you need. You could do like width and length if you want. And so if that's called W, this is called W. But it's not going to be straight up regular perimeter where it's 2L plus 2W. In this case, perimeter, we'll use P for perimeter, would be 2 of the widths and then only 1 of the lengths, since we don't need this side with fencing. Okay, remember, we need 180,000 square meters, okay, is like contained. That's the area, right? So that's going to come up as our secondary equation, because if you take a look, like, this is great. You did a good job so far, but it has 2 variables on this side, and so not really the easiest thing to take a derivative of. So let's try to get it down to 1 variable. So we're going to use a secondary equation, okay? And our secondary equation here would be if this area, aka length times width, has to be 180,000. That's something that's definitely important here. Then solve for W or L. I solved for L, so I'll stay with that. Divide by W on both sides. And then I'm going to plug that in, again, similar to last time. Substitution here. L is the same thing as this. So now I have P equals 2W plus, and I'm going to rewrite this, guys, as 180,000 W to the negative first, if that's okay with you, just for the sake of taking a derivative. There we go. So instead of L, I wrote in that. And now I take the derivative, right? I'm trying to find the minimum, meaning I need the first derivative set to 0 and solve. So that would give me 2 plus, bring down the power, so technically minus 180,000 W to the negative second. Okay, you would end up solving this. I'm sorry, so you set it to 0, and then I'm just going to start solving. So if I add over the 180,000 over W squared, I'll rewrite it this way. Basically, you just have to do a little algebra here. If you kind of cross multiply 180,000, I don't want to spend a lot of time on the algebra, since hopefully you feel okay about that. W squared is 90,000. Therefore, W is plus or minus 300. Hopefully you realize we can't have a negative width, so just 300, okay? And again, to confirm this is true, I'll kind of shrink down my work here. Again, process here, found the primary equation, used a secondary equation if available to help get us down to 1 variable, took the derivative, set it to 0. That's really what happened right here. Okay, and then we added 180,000 over W squared to the other side, solve for W, etc. And the last step is, it says what dimensions, so we need width and length. So width is 300, and then length, you could plug in 300 right here. 180,000 divided by 300 would be 600, and this is in meters. All right, and that is the least amount of fencing, right? So if you were going out to buy fencing, yeah, you could do a lot of different dimensions to get you 180,000. But if you went to the store and you're like, I want to spend the least amount to get a bargain for how much fencing I need for this pasture, 300 by 600 would be the least amount of fencing you could get. So we're going to try one more example here. It says an open top rectangular box is constructed from a piece of cardboard that's 10 by 16 by cutting out congruent squares from the corners and folding up the sides. Find the dimensions of the box with the largest volume. Okay, first of all, largest volume, that's going to be that thing that we are maximizing, right? So this is that primary equation. We are looking for the max volume, and volume of a rectangular box, we could already write that down. Primary equation here would be volume equals length times width times height. Okay, let's figure out what this looks like. It says it was originally just a piece of cardboard, and that cardboard was 10 by 16. Okay, then it says we cut congruent squares from each of the corners. So take a look at what would happen here. Okay, if you took this, I'll use a little dashed line to show I'm cutting. Cutting out corners, cutting out corner, cutting out a corner, cutting out a corner, and those corners, when they're gone, you know, your shape will look something like, sorry, I want to go back to my regular pen here. Hopefully you can kind of picture this. It's not my best drawing ever, but that's what the piece of paper would look like, okay? And let's say we named all these little pieces X. We don't know how big these are that we cut out. So Now, what you're really thinking about is if you fold this guy up, so take this, fold up the sides. So you're going to fold, you know, right here, right here, right here, and right here. Now, my new little figure would be something like, you know, this would be dashed, it's behind kind of, there we go. Okay, so this is the final picture, and these dimensions would be these bottom dimensions here. All right, now, biggest thing you have to figure out is from this picture, you have 16, what would this be right here, right? These dimensions, because these dimensions end up being the length and width of this rectangular box. Okay, so if I have 16 and I take away x from this side, and I take away x from this side, this would give me 16 minus 2x. Okay, this whole thing was 16, took away x from the left, took away x from the right. And same thing over here. What would this be? Well, I had 10, I took away x, I took away x, so 10 minus 2x. Okay, and hopefully you can see where that lands. Oops. Right here, 10 minus 2x, this is 16 minus 2x. This is right here, 16 minus 2x, this is 10 minus 2x. And then finally, what about the height? This would be x, right? Because if you fold these sides up, these were x. Now this rectangular box is x tall. So your three dimensions here, the length was, 10 and 16 you could interchange, but 16 minus 2x, then you had 10 minus 2x, and the height was x. Okay, so this setup here, I would argue that your secondary equations technically, right, would be, you know, if you wrote down secondaries, you don't have to do it this way, by the way. This is just kind of a nice way of organizing, would be how can I replace these? Well, length is 16 minus 2x. I have another secondary that's 10 minus 2x, and I also know the height is x. So arguably, those are your secondary equations. All right, so same process we've been doing. We're going to take the derivative. We notice we have a bunch of stuff multiplied together. Just FOIL this out. So I'll FOIL these two first. 160 minus 20x minus 32x plus 4x squared. I still have an x out there to distribute in. All right, what do we got? 4x cubed minus 52x squared plus 160x. Okay, so take the derivative. We've got 12x squared minus 104x plus 160. All right, and we can take out we're going to set it to 0. You can take out a 4. I've got 3x squared minus 26x plus 40. And your favorite, we get to factor 3x minus 20, and this would be x minus 2. What multiplies to, depending on how you do this, you know, you want these two numbers to multiply to 40, and then the middle two, kind of that middle part of FOIL, to add to negative 26. So we solve this and we get 2 and 20 over 3. Okay, sometimes there can be two answers, but you want to double check here. If you plugged in 2, that would work, right? They're both positive numbers. If you plugged in 20 thirds, right? 20 thirds is about, it's almost 7, right? So it's 6.6666. And if we take those and plug that in, so if you plug in 6.6 here, 10 minus 2 times 6.6, that would give me a negative side length. So 20 thirds is too big of a number. All right, so to finish up here, you're just going to write the dimensions. That's what it was asking for. Find the dimensions with the largest volume, aka plug into right here in this picture. And you can use your little secondaries right here. So if we plug in 2 as our final x value here, so the height is 2. Again, I said length was 16 minus 2x. I think you could interchange those. Length and width you could interchange. Length would be 16 minus 2 times 2, which is 12. And height, nope, not what I've left, width, 10 minus 2 times 2, which is 6. Okay, and I believe this was in inches, so I could write that down. All right, easy way to double check your answer. Okay, plug it in and make sure that they're all positive numbers and make sure that those dimensions make sense. So again, that is it. We'll try example 4 in class. Thank you for watching, and let me know if you have any questions.